In this video, we'll talk about the idea of the definition of the derivative, which is one of the main core concepts of first semester of calculus. The derivative is going to form the basis for most of what we're doing for the next couple of months, or couple of chapters for sure, in terms of calculus concepts. So what is the derivative? Well, the derivative is the slope of the tangent line to the graph of a function. So if I have a function f, the derivative of f at a point A is the slope of the tangent line to the graph of f at this point, provided it exists. Now this idea is something we have discussed previously, this idea of the slope of the tangent line. We talked about it before in the context of using limits to approximate things, and how we could use the slopes of secant lines taking a limit to get to the slope of the tangent line. And that's the same thing that we're going to do here for this derivative. So we're going to get here via slopes of secant lines and limits. The idea which is illustrated in this example here. We can see if we take 2 points, P and Q, we can find the secant line between them. We could compute their slope. But the point is, as we move Q closer and closer to P, we're getting lines that are going to slowly approach a certain slope that's going to be the tangent line. That is, if I limit the point Q to approach P, I will get a way to figure out the slope of this tangent line from the slopes of these secant lines. How do we actually find this slope? Well, let's write out what these points P and Q are and figure out how to find the slope of that secant line. That will then take a limit of to find the slope of the tangent line. So here, the point P is located at a comma f of a, and we'll define the point Q here to be at a point a plus h. So h is going to be some parameter that we're using to denote how far apart these points are. The point Q here is at a plus h, f of a plus h. That means I can find the rise and the run for this setup based on these differences here. So the rise for the change in y is f of a plus h minus f of a, and the run is a plus h minus a, or just h. This means that in this case, the slope of the secant line is given by f of a plus h minus f of a all over h. And if we want to limit the point Q to approach P, I need to send h to 0. The slope of the tangent line is given by the limit as h goes to 0 of f of a plus h minus f of a all over h. And this here is our derivative of this function f at the point A. That's the formula we will use to work out what this derivative is at the given point. So to collect our definition here, the derivative of function f at a point A is the slope of the tangent line to the graph of this function, and it is computed by limit as h goes to 0, f of a plus h minus f of a all over h, and that will give us the derivative at this point. Now note here, h could be negative. This is a two-sided limit at 0, and if we just take h negative, we're taking points to the left of p, not the right of p. It works out the same way. As an example of how this works, find the slope of the tangent line to the graph of y equals x squared at x equals 1. This means we're taking our function here, f of x is going to be x squared, and a is going to be 1. That's the point we're taking the tangent line. So then our slope of the tangent line, this is the derivative, is given by the limit as h goes to 0 of f of a plus h minus f of a all over h. Now we can plug in what f is. This is the limit as h goes to 0 of 1 plus h squared minus 1 over h is the limit as h goes to 0. I can expand out that squared. 1 plus 2h plus h squared minus 1 over h. 2 1s here will cancel, leaving me with limit h goes to 0, 2h plus h squared all over h. I can then cancel an h from every term because I can factor an h from the numerator and cancel it out. That cancels that, which gives me a limit as h goes to 0 of 2 plus h, which equals 2. Therefore, I can conclude the slope of the tangent line at this point is 2. So that's an example and how we compute the derivative of a function at a point gives us the slope of the tangent line there, and we have a method for working out what that slope should be from this definition of the derivative.